This video is on applying Newton's second law of motion to springs. Hopefully we will learn a lot more about springs when we learn about energy and simple harmonic motion. Unfortunately, there isn't a lot we can learn about springs when learning about forces only. Question 1. Explain what is meant by the equilibrium position of a mass attached to a spring on a horizontal surface. So imagine you have a mass attached to a horizontal spring at the equilibrium position x equals 0 when it's at rest. You stretch it to x equals a, the spring. The mass oscillates between x equals a and x equals minus a. It just goes back and forth. In the equilibrium position, the mass is in dynamic equilibrium. Remember the meaning of dynamic equilibrium. Sigma f is 0, a is 0, v is constant. Please memorize this. Remember the meaning of static equilibrium. Static equilibrium is sigma f is 0, a is 0, v is 0. Question 2. What is the equation for the spring force? Define each variable. What is the name and what are the units of K in the spring force equation? So this is called Hooke's law, H-O-O-K-E-S. So the force on a spring is F equals minus K delta X, where F sub spring is the spring force, has units of newtons. Delta X is the displacement from equilibrium. It could be positive or negative. K is a spring constant. It's always greater than 0. So if the spring constant K is big, then the spring is very stiff and it's very difficult to get it to be pushed or pulled. If the spring constant K is small, then the spring is weak and it's very difficult. Then it is very easy to pull it or push it a great distance. The negative sign is the restoring force. That means it returns the mass on the spring to the equilibrium position. So imagine you release the mass at this position, x equals positive a. X is positive. Positive times a negative is a negative, so the force is negative. So if you're to the right of the equilibrium position, the force is negative. That means the force brings the object back to the equilibrium position. Now imagine if this mass goes all the way to x equals minus a. If the mass is at x equals minus a, delta x is negative. According to this equation, a negative times a negative is a positive. So the force of the spring is positive. That means it's to the right. So the spring is pushing the mass to the right. So this negative sign is always trying to bring the mass back to the equilibrium position or to the middle. Question 3. Label the forces on a mass attached to a spring on a horizontal surface which is stretched a distance a from its equilibrium position and then released. So imagine the block is at rest at x equals 0, but we pull it to x equals positive a. Once you release it, what forces are on the object? You got normal force, gravity force, force of the spring, which is Hooke's law, and force of friction. Question 4. Draw a force versus displacement graph for a mass on a spring. What does the slope of a force versus displacement graph tell us? What does the area under a force versus displacement graph tell us? Where did I get this graph from? I got it from this equation, F equals minus K delta X. So if we're going to graph F equals minus K delta X, it's going to look something like this. So the slope has units of newtons over meter. That tells us the amount of force needed to achieve a certain displacement. It tells us about the stiffness of the spring. And the area under the line has units of newtons times meter. These are the units of energy and work. So the area under the curve tells us the work done on the mass by the spring. Once again, we're going to learn a lot more about springs later, hopefully.